This is screencast 2 for week 5 of Business Administration 571. Beginning for this week is the topic individual observations chart. As I mentioned last time, that also goes by the name of an X chart without the bar, not X bar, just an X chart. And the distinguishing feature is subgroup size n equals 1. Thus the name individual observations, because the subgroup is simply a single observation on your process metric. So first, how do we build this chart? Ryan recommends that K be greater than or equal to 300. This is stage 1. So 300 observations in stage 1 before computing X bar and S. Then compute sigma x hat with S over C4, where K is used instead of N in table E to look up C4. You still have a bias correction that you need to perform. Problem. Table E has n less than or equal to 25. But Ryan say we need to have 300 or more before we should be trying to compute mu hat and sigma x hat. Notice that there's no bar up here on X. So what should we do? Okay, so first, be clear about one thing. I'm going to take all my stage 1 data and I'm going to compute S, and then I'm going to divide it by my bias correction factor C4 using K instead of N, because my subgroup size, as far as the C4 value is concerned, is all of the observations in stage 1, because I'm not subgrouping, because I'm just taking the original data. And notice that with an X bar chart, I do this. But I don't need to do this averaging because I don't have subgroups. I just have one computation of S. So with X, with an X chart, S equals the square root of 1 over K minus 1, sum I equals 1 to K of xi minus x bar. The classic definition of the sample standard deviation. because I'm not computing within subgroup standard deviations. Why? Because I only have one observation in each subgroup. So just to be clear, note, you can't do this. See, because you get this. This is a no-no. So this doesn't work. So we don't compute within subgroups because subgroups are of size 1. Moral of the story, if you want to compute the standard deviation, you need 2 or more observations. But Ryan is saying, I want to see 300. So what are we going to do if we can't use the table to get C4 because it only goes to 25? I know. Let's use an approximation. So I'll put a little wiggly sign on the top of this equality because it's not really that, but it's pretty close. And it's 4 times n minus 4 over 4n minus 3. And this is good for n bigger than 5. I thought we were working with k, you're thinking. How come we're back to n? Well, this is an approximation to C4 using the nomenclature of Table E. And in Table E, subgroup size is n. So here's a lecture question. See how well C4 is approximated by this formula by computing it for n equals 6 and 10, and comparing it to the values in Table E. So you might be thinking, is k bigger than or equal to 300 realistic? Well, we've kind of backed into what I should have brought up in the first place, and that is, why are we doing this? What's wrong with an X-bar chart? Well, an X chart is appropriate if A, units are expensive and any production problems therefore need to be fixed before many non-conforming units are built. Are built after a signal has been received. So what was the old police rule for a serial killer, a shooter in a public place? The old rules were to call for backup. What are the new rules? The new rules say, look, if you are a law enforcement officer and you receive a message that there's an active shooter, say on a campus or in a shopping mall, you are now instructed to risk your life, go in and start shooting as fast as you can at the suspected shooter, and only later, well, or have someone else call for backup. Why? Well, new law enforcement policy is An active shooter is so deadly and so many people are being killed that there's no time for backup. In our case, we're doing something, making something, possibly, for which the consequences of letting time go by while making non-conforming units. We'll never make non-conforming units. No, you will if something's gotten out of whack on your line and you don't know it because your chart's taking its sweet time to give you signal. You will be making non-conforming units. So the idea is, for a process that has very expensive units that are coming out, you want to have a system that will flag a problem before very many of them get built. An X chart then is just what you need. And an example is a Ferrari. They build at their Modena plant. For all their efforts, they build 10 cars a day. You could compare that, I think, to how many Ford Focus cars Ford is able to build in a day. It's a whole lot more. So Ferrari, building a very expensive unit and building them slowly, they don't want to wait for subgroup sizes of 10 to build up before they plot a point on a control chart. They want to be plotting a point every unit. See, with 10, they would have an entire day's production possibly go out the door from a production line that has, say, the crankshaft sub-production line being in a state of out of control. That would be pretty catastrophic for purposes of having to recall and to replace the engine. So we should always do this, you're thinking, because it's got to be better to have earlier signals than later signals. Well, the out-of-control ARL for an X chart is always a little bit worse than an X bar chart. So the X chart is never going to be as good as an X bar chart. You're always going to do better as far as your the number of subgroups it takes to have a signal happen if you're running subgroup sizes that are bigger than 1. But remember, the X bar chart is accumulating a large number of units in order to get even one subgroup, whereas an X chart isn't accumulating anything. But the bigger problem is this. The central limit theorem is silent on the normality of the plotted metric. Who cares? Well, you do, because the control limits of an X chart are built using this formula. You could probably guess what it is, but here it is in all of its glory. So it's just the same old formula, except instead of using sigma hat x bar, we use sigma hat x. Why? Because x and x bar are the same thing. What's the sample? What's the average of the value 14? Dumb question. Well, you only gave me one number. Yeah, but what's its average? Well, its average is 14, because you add up all the numbers and divide by how many you got. I got one number, so that's that number. I added them up, then I divided by 1. So you can take the average of one number. It's important to keep that in mind. So x and x bar are the same thing with an x chart. And it uses this formula. This formula is coming from the normal distribution. So checking for normality is super important. Observed metric. Is more important with an X chart than with an X bar chart. So always construct a normal QQ plot of stage 1 observations when building an X chart. Transform as necessary. So I left a question hanging, and that is this K bigger than or equal to 300 realistic? Well, if you're at Ferrari, you've had a wonderful turn of events in your career, and you've been hired as a supply chain analyst at the Ferrari factory, and they've brought you over and they've gotten you Italian citizenship, and you've taken intensive courses in Italian, and so you're working there, and you decide that you're going to put in an X chart on a critical metric on the Ferrari line. Maybe it's door fitting. Doors have to fit perfectly, and there's this one metric that measures how far off a door is when it gets shut from where it's supposed to be. And you say, I'm going to do an X chart. Okay, so you open up your book, and Ryan says you need 300, and so you're saying, oh, that means I need a whole month of production, 10 cars a day, 30 days. I don't think that's going to fly at the level of senior management. So how many points do I need? Well, I think 300 is a little bit excessive. I can see why Ryan wants to have a nice big giant sample size, but in practice, if units are time-consuming to build, okay, somewhere around 30 may be all you can afford. But you certainly want to have more than 10 if you can get away with it. Okay. You're thinking, well, that's pretty simple. I don't see an issue there. Unfortunately, there's a big issue with this idea. Big issue is what I'll say then. Because I said big issue. Big issue is this. Well, an X-chart is sensitive to both mu shifts and sigma shifts. You'll remember the way we detected shifts in sigma was with an S chart. You're thinking, well, okay, I'm there, I'm on it. I'll just run an S chart in conjunction with an X chart. No can do. An S chart cannot be maintained because n is not greater than or equal to 2. So you can't run an S chart, because I just said a little while ago, you'll get 1 over 1 minus 1, and that's a no-no. So Ryan notes several authors. So I'm anticipating your solution. Ryan notes several authors arguing against the use of an R chart alongside an X chart. Yeah, I know you're going to say, well, just if S chart's out of reach, I'll just run an R chart, because I can always run an R chart, because it's just differences between two successive observations. Well, folks have looked into that, and they have found, unfortunately, that doing so doesn't give you the sensitivity you need between the two charts to distinguish between a mu shift and a sigma shift. So, in other words, if you get a shift if you get signal off of an X chart, you won't know if it was a shift in the mean or a shift in sigma. And running an R chart really doesn't give you separate signals between whether you have a mean shift or a sigma shift. It has been found through both through simulation and through empirical experience. So we have a problem, and that is, if we run an X chart and we get a signal, we don't know whether it's because the mean has shifted or whether the standard deviation has shifted. Our correction, our out-of-control action plan, will be very different depending on whether we're chasing a mean shift or we're chasing a degradation in variance, which is almost always an increase in variance. So I will go into this problem and its solution in more depth in the next screencast.